Welcome to this edition of Crydom TechLab. This edition of Crydom TechLab will explain how operating conditions of solid-state relays and contactors impact their output rating. Solid-state relay and solid-state contactor output ratings are based upon their design and materials, as well as the external operating conditions where they are installed. All SSRs and SSCs utilize power semiconductors, which generate power as a result of their on-state voltage drop or resistance when carrying load current. For AC output relays utilizing thyristors, power measured in watts equals forward voltage drop times load current. For DC output relays utilizing field effect transistors or FETs, power measured in watts equals load current squared times on resistance. To ensure reliable operation of the SSR or SSC, this power must be dissipated into the surrounding environment so that the relay operates below its allowed maximum temperature. Variables such as the type of semiconductor, duty cycle, heat sinking, and surrounding ambient all affect the temperature of the SSR or SSC, and therefore the load current allowed through the relay. Generally speaking, SSRs or SSCs carrying more than 5 amps of load current will require some amount of external heat sinking in order for them to operate correctly. During this TechLab episode, we'll discuss the relationship of the 3 most significant variables: load current, ambient temperature, and heat sinking, and show different methods to determine one of these variables when the other 2 are known. Note that the load current rating of the SSR or SSC is always marked on the relay, but owing to the limited printing area available on most SSRs and SSCs, complete ratings and conditions may not be fully described on the relay itself. To ensure the proper selection and use of SSRs or SSCs, product specification sheets accompanying the relay or available on the manufacturer's website should be reviewed carefully to ensure a full understanding of the relay's ratings and associated conditions. Most panel-mounted SSRs or SSCs' maximum output current ratings are based upon 100% duty in a given ambient temperature when mounted on a particular size heatsink. For example, this Crydom D2425 SSR is rated for continuous 25 amps RMS load current in a 40 degrees C ambient when mounted on a 1 degree C per watt heatsink. But what if the conditions of application for this SSR are different than these parameters? The relationship between these parameters is demonstrated by the following model, where on the chart A is the selected SSR with specified thermal impedance, forward voltage drop, and maximum allowed internal operating temperature, where TJ max is approximately 125 degrees C for thyristors and 150 degrees C for FETs. B is the thermal interface material placed between the SSR and the heatsink and its specified thermal impedance, typically between 0.02 and 0.1 degrees C per watt. C is the calculated minimum heatsink thermal impedance rating in degrees C per watt required for proper SSR operation. And D stands for the operating environment's maximum ambient air temperature in degrees C. From the model, it can be seen that there are 3 thermal impedances which act in series: output semiconductor to relay baseplate, thermal pad or interface material, and heatsink impedance. Lowering any of these impedances serves to reduce the relay's internal temperature, and conversely, increasing any of them tends to raise the relay's temperature. The ambient temperature acts directly on the relay's temperature, increasing and decreasing it in direct proportion to the surrounding ambient air temperature change. Forced air flowing over the heatsink effectively decreases the heatsink's impedance, thus reducing the relay's temperature. Forced airflow over a heatsink is the subject of another TechLab video. For those who would like to calculate the exact values of any of these parameters, the mathematical relationship between them when solving for heatsink thermal impedance rating in degrees C per watt is as follows: heatsink thermal impedance equals maximum die temperature minus ambient temperature minus the product of the relay's thermal impedance times the power dissipation in the relay, all divided by the power dissipation in the relay. This formula can also be manipulated to solve for ambient temperature or power, and thereby the maximum allowed load current for those conditions. Fortunately, SSR manufacturers' specification sheets, like the Crydom D2425, often include an output or load current thermal derating chart that simplifies the relationship between the ambient temperature and allowed output current for several different heatsink ratings. There are two versions of these types of charts, a two-step version and a single-step version. As can be seen in this single-step chart, increasing the ambient temperature decreases the allowed load current. It can also be seen that reducing the heatsink rating also reduces the allowed load current. This same behavior can also be read in two-step charts by following the selected load current to the right side of the chart and choosing a heatsink that will allow achieving that rating in a given ambient temperature. Either of these two charts is a simple, straightforward, and convenient means to coordinate the three main variables of allowed load current for a given heatsink and ambient condition. And finally, the simplest means to select a heatsink is to use special software tools created for such purposes, like the Heatsink and Assembly Selection tool available at the Crydom website. This tool will help you choose a suitable heatsink for your relay, considering the parameters of your specific application. For detailed technical information, including the selection and use of heatsinks, thermal interface material, and forced air cooling, visit our online tech library at crydom.com or contact Crydom Tech Support. Thanks for watching this edition of Crydom TechLab.